Okay, so now it is a problem 6 for the simple 2 of our final exam. So it asks us to find the center mass and the central mass moment inertia of the composite object. Okay, so before we get started, probably the unit here. So it may be a little bit confusing here because we sometimes see that pound it's for the it is actually unit for force, but here actually it is a pound for mass, and to differentiate that from pound for force, so we we have m here, meaning that it is a pound for mass. So how it is related to pound for force? So actually here we see that it is related to pound for force by, so we have a 1 pound for force equal to 32.2 pound for mass times weight divided by uh square second. So okay, so in other words, you can divide that if if you have the pound, if you have 1 pound for force divided by the corresponding gravitational acceleration in feet per square feet per square second. So it is 32.2, okay, feet per square second. And you're gonna see that it actually equals to 32.2 pound for mass. Okay, times weight divided by square of second, and then divided by the gravitational acceleration. So you're gonna see that, okay, the 32.2 will be canceled out, and the feet per square second will be canceled out, and you're gonna see that you are going to have 1 pound for mass here. In other words, it is seen that 1 pound for mass equals to 1 pound for force. Okay, times second square divided by weight, right? Okay, so the reason why we are seeing this is because firstly, the pound for mass, pound for weight, sorry, it is a pound for mass, pound for force, it is confusing. Okay, so but in practical engineering, they are widely used here. And secondly, it is to stress when we are seeing that when we are mentioning the unit for mass here, so sometimes in our calculation we will have acceleration, and we are going to go ahead to calculate force in the future. If you learn that if you are learning dynamics, okay. So in that way, we need to know that if we see pound for mass, what is the unit of length related to that? Here it is answered. It is actually feet here. Okay. So now if we go back to check the unit of length in our problem, it is a feet. So that means the unit of length and the unit of mass, so they are consistent here. Okay. So now, okay, we can go have to approach that, and we've already made sure that the problem is in the unit system of pound for force and weight second. Okay, okay. So now the first question asks us to find the location of the center mass, and how can we approach that? Well, so we know that the center mass, the conceptually, it is very similar to centroid, right? Okay, so the center mass of this composite object, it is calculated by weighted average of the center mass of each part, right? So the center mass YG actually equals to weighted average, right? Is a mass I. It is the mass for the S uh, part of the composite object times y bar gi, which is actually the location of the center mass of each part, divided by total mass here. Okay. Now, we see that the object is composed of two parts, right? It is the rod and the sphere. Please note, it is a sphere, not a circular plate. Okay, so it will determine which formula we are going to use in the second part of the problem. Okay, so if we go with the first part, the mass equals to 2000, right? The mass equals to 2000 pound. And then the location of the center mass for the rod, it is located as at the very center of the rod, right? So it is so the head is just a half of the total head. It is 5 feet here, right? So it is 5 feet. Okay. So now second part, the mass here is 10,000, right? It is 10,000. Okay. Times the location of the center mass for the sphere. It is located at the center sphere, right? And the location is, it is the total length of the rod plus the radius of the sphere, right? Okay, so it is actually 13. Then divide by the total mass. Okay, so you see that it equals to, okay, we have a numerator to be 2000 times 5 plus 10,000 times 13 divided by 12,000 here, right? So it is 11.67. It is a fit. Okay, so it is answer for the first two questions here. Okay, so now second question here is to determine the central mass moment inertia of the object. How are we going to approach that? Well, we first denote the location about where we are going to evaluate the mass moment inertia. Okay, and then the way how we are going to approach to evaluate the mass moment inertia of the composite object is to make use of parallel X theorem, right? So we know that the total mass moment inertia of the composite object equals to summation of the mass moment inertia of each part, right? And the mass moment inertia of each part equals to the central mass moment inertia of each part plus the mass of each part times the square of the distance between the center mass of each part to the location where we are evaluating the central, where we are evaluating the mass moment inertia. And here it is actually the center mass of the entire composite object. Okay. Once we know that, we can go ahead and evaluate that. Part one here is the rod. What is the central mass moment inertia? Well, we can go to the appendix. So now go to the appendix, we see that the central mass moment inertia of the rod, it equals to 1/12 times the total mass times the square of the length, right? Okay. So we have it here. Okay. So the central mass moment inertia of the rod equals to 1/12 times the total mass. It is 2,000 pound for mass here. Then times the square of the total length, it is a square of 10, right? Okay, it is 10 feet. Then plus the total mass of the part one, 2,000 pound. Then times the distance between. Okay, so it is a distance between the centroid of the rod and the central. Actually, it is a center mass of the rod and the center mass of the object. So it is this distance here and that equals to actually the difference between the y coordinate of the center mass for the rod and the center mass for the composite object, right? So it will be the the coordinate of center mass of the part which is at fab, right? Minus the coordinate of the entire object, which we already have. It is 11.67, and the square of that. Okay, so it is a mass moment inertia of the rod. And second part is the sphere. So again, we can go to the appendix to check the central mass moment inertia of the sphere equals to 2/5 times the total mass times the square of the radius, right? Okay, so it is a 2/5 times the total mass. It is a 10,000 times the square of the radius, which is actually square of 3. Okay, and then plus the total mass of the sphere times the square of the distance between the center of the sphere to the, sorry, it is a center mass of the sphere to the center mass of the object, right? It is this distance here, and it can be similarly evaluated as the difference between the y coordinate of the center mass of the sphere, which is at 13 here, and the coordinate of center mass for the object, 11.67 square of that. Okay, now we can go ahead and evaluate that. It equals to, okay, for the first part, the rod, it is 1/12 times 2000 times the square of the length plus, okay, parallel x theorem. So we have the mass moment inertia equals to, okay, it is a little bit big. It is 805,644.47 here. Okay, so the second part, it is the sphere here. It's the 2/5 times 10,000 times the square of 3, which is actually the radius. And then 10,000, the total mass, times the square of the distance between the two center of mass. Okay, so we have it equals to, it is 50, it's 53,689. Okay, so now we take the summation of the two. It is actually, okay, it is 159,333.47. So the unit here, well, the unit here is a little bit tricky. You can write it to be, okay, you can write it directly to be pound for mass times square root of feet. Okay, so the unit of mass moment inertia, it is always the unit of mass times the square of the unit of length here. And please note that you can also express it as, okay, since the pound for mass is actually pound for force times it is a square of the second divided by weight, and then you have the weight square here. It is actually equals to pound times second square as well. Both are correct here. Well, knowing this may help you in dynamics. Okay. So when you are analyzing if the object is subject to the moment when it has started to accelerating rotation. Okay, so in that case, this kind of concept can be extremely helpful. And another interesting to note that although for our sphere it is so the mass is significantly larger than the rod, but its contribution to the central dome mass moment inertia is smaller than the contribution from our rod. So the reason is because the mass moment inertia actually it is a quantity to express how mass is distributed over the space. So it is so for specifically for this problem. So we see that the mass for the rod it is distributed far from the central mass of the object. So therefore, the mass of the rod contributed more to the central mass moment inertia here. Okay. So this problem, the problem 6, it is actually examining the evaluation of center mass and mass moment inertia of the composite object. For center mass, it is actually a weighted average of the center mass of each part. Well, it is conceptually very similar to centroid. But for the mass moment inertia, so to compute it, it is a here we need to be familiar with parallel X theorem. Okay, and then we can calculate the mass moment inertia of each part of the object and take summation of that.